Hello all, I welcome you all to the 11th lecture in this course E614. So in the previous lecture we discussed about PN junction, and then we derived certain important parameters like electric field, potential, the width of the depletion width and so forth. Right. So we found the width W to be root 2 epsilon S being the dielectric constant, Q the charge, Na plus acceptor density, donor density, right, into V0 being the built-in potential, right. We saw the expression for V0 and we saw the expression for the electric field, right. So we know that V0 is half E max, electric field, maximum electric field, into width of the depletion, right, and maximum electric field we found to be Q ND Xn by epsilon S, which is same as Q Na Xp by epsilon S. Xn and Xp are the extents of depletion within the N type and the P type region, right. With these given, I'm going to make a simple substitution. I'm going to make something like NB is NA by Na plus Nd. This is useful because in the event if Na is very much higher than Nd, you can see that Nb will be equal to Nd. And in the same way, if the other way around, right, if Nd is much larger than Na, so basically Nb is in a one-sided junction, in the sense that if any one of them is much larger than the other, then Nb will be equal to the one which is smaller, right. So now with this given, I'm going to, so we can rewrite W 2 epsilon S by Q NB, right. But then we know that it is actually 2 kT by Q, right. This 2 kT by Q comes because of the fact that we have neglected in the original derivation, we have neglected the majority carriers in the depletion width, which is not always true, and if you include them, then you will get this for the correction in mobile charges in the depletion width, right. With this given, you have what is called as the d by length. So this can be rewritten as LD being the d by length root 2 beta V0 minus 2, where beta is Q by kT. This is typically used in thermodynamics, where beta is called this temperature equivalent of the energy, right, and Q is used because we are using it in conjunction with the potential. So basically beta is Q by kT. It is the thermal energy, so to speak, right. And LD being the d by length is given by root of epsilon S, the electric constant of silicon, Q NB into beta. So basically, why is this d by length very important? Because this is typically seen in any places where you have electric field and charges. Basically, physical meaning of d by length is the length at which the potential, any potential is screened. So if you have a metal and you have a applied potential over the metal, it is screened in the length extent of a d by length, right. So this is typically used when you have what is called as a d by C equation, where it is del square V is 1 by L square V0, something of this sort, V, right. So you can see that this is a differential equation, and it reduces as 1 by LD square, where LD is given by this, right. So besides all these things, it is just very important in semiconductor physics because it tells us the extent in which the charge carriers and the potentials are dominant, right. So we will see the effect of doping density and the temperature for silicon, right, and its impact on the d by length. So here I have d by length against the doping density, and you see it is all in angstroms. So basically, if you have a very high doping density, then you have a debye length which is significantly smaller. So what it means is that if you have lot of charge carriers, then the electric potential is screened out much faster. Whereas if you have a very small charge carrier, very small doping density, then you have the potential penetration into a material to be much longer, right? This is what another way of calling this is called the Thomas Fermi screening, but then we are not going to go there right now. It is just a parameter LD which tells you what is the length at which the potential is getting screened, right? And it depends upon the temperature and the doping density that is under consideration, right? So with this, let us go back to our previous discussion. Right. So we have length in terms of we have the width in terms of the debye length, and now let us take a look at the various aspects of, let's say, the depletion width in terms of the temperature and the applied potential, right? So now, till now, we have seen the junction at equilibrium, right? Now we will have the junction with an applied bias. So the width here, this expression is used when you do not have any applied potential, and V is the inbuilt potential, right? So if I take this PN junction and apply a potential V, so the question is, what happens to the depletion width, right? So this is again a very simple extension of the derivation that we currently had. So the actual width of the depletion under this condition, where you have an additional potential, is LD root 2 beta V naught minus V. In terms if you have so it becomes positive when you have a forward potential, that is positive bias to the P, and it has a positive potential. Okay, let me go through this. Okay, minus 2. This is the expression for the width. So if you apply a positive potential to the p-type junction, then you have what is called as a forward bias, where the width reduces, right? It is V naught minus V. Or if you have a negative potential to the p-type junction, then you have what is called as a reverse bias, where the width actually expands. So as you apply more and more negative potentials, the depletion width is going to raise, right? So now we will have now let us see the plot for the width of the depletion against the applied potential and at various temperatures, right? I hope you are able to see, right? So we are plotting the depletion width here, right, versus the doping density and applied and various applied biases. You have a line here which is shown in dotted lines. Okay, this is the actual depletion width at zero bias potential, and you have the increasing density NB. Right? You can see that as NB rises, your depletion width should reduce, right, which is normal because that's from the expression that is straightforward, right? And if you reduce the potential, let's say if you apply a positive bias, here it is shown to be 0.1 positive bias, right? So in this situation, let us say this is VB minus V, right? So you have a reduction in the depletion width, whereas if you apply a negative bias, in the sense applying a reverse bias to the junction, you will have the junction depletion width increasing, right? At higher and higher potentials that are being applied, you can see that the depletion width increases. There is another interesting aspect here which is shown, which is called as the breakdown voltage, right? You can see that the junction starts to break down at higher potentials and higher doping densities, right? Can you think about why this is happening? Basically, breakdown voltage is is the potential applied by across the length dimension at which it is applied, right? So if you see that as the doping density increases, the depletion width reduces. The same potential line applied to different doping densities, meaning reduced depletion widths, will break the dielectric, break the space charge region at a much smaller potential, right? So basically you can see the breakdown happening here for 10 volts, it is happening here for 100 volts, and it is happening here for 1000 volts. Basically 1000 volts will break down at much lower density, whereas 10 volts breaks at much higher density, right? So basically this is the conversion in which you can have the maximum field that can be applied across a PN junction diode. We will deal with breakdown more in detail later, but here we are just showing this because it's an expression against the depletion width and the doping density at various applied potentials. Right. So now that we have discussed the effect of applied potential and the doping density, on the doping density is being given by the d by length, right, on the actual width of the depletion width that we saw. Right. In addition to this, what you have what is called as the depletion capacitance. Right. You have, it's a capacitor because of the fact that there is a region which does not have any mobile charge carriers, and it is engulfed by regions which have very high charge density in comparison. Right. So basically this is an equivalent of a metal insulator, metal junction, which is a capacitor for all practical purposes, right? So this particular structure also has a capacitance. And what's the typical definition of a capacitance? Is the change in the charge which is accumulated at the junction by the applied potential across the junction. Right? V0 is the built-in potential. Q is the charge enclosed between these two plates. This is the charge which is uncovered, or charge which is depleted, right? So how do we find this ratio? We know that the charge is Q into NB into W, right? NB is the effective density that we saw before, and W is the width of the depletion, right? And the applied potential or the built-in potential is Q W naught square NB by 2 epsilon s. We saw this before. So how do we get this particular expression? You see that both of them has width, so I'm going to take dq by dw and divide it by dv by dw, right? If you do this, you can easily see you will get qnb by qw nb by epsilon s. So basically this expression will come out to be epsilon s by w, which is sort of understandable, right? Because you just have a parallel plate capacitor, and then the capacitance is epsilon A by D, and of course this capacitance is per unit area, right? So if I have the areal incorporation to this, you will see the same value, right? It should not be surprising. And we know the expression for a W, so if I substitute this, the actual capacitance will turn out to be 2 root 2 epsilon s NB by 2 into VBI plus or minus V, depending upon the applied, whether it is a positive or reverse bias, right? Minus 2 KT by Q, which in other words is epsilon s by root 2 LD, LD being the depletion width, root beta VBI plus or minus V minus 2, again from the previous substitutions. So you can also write this as 1 by c square. I will show you why we need to have this particular term. 1 by c square will turn out to be 2 LD square by epsilon s square beta VBI plus or minus beta V minus 2. Right? And if I do this d by dv here, remember this VBI or V naught, whatever that we have used till now, let me put it V naught, right? And this V is the applied potential. This is different from the built-in potential, right? V is the applied potential. So if I do this 1 by c square by the applied potential V, we will get 2LD square by epsilon S square into beta, right? And which will turn out to be 2 by Q epsilon S. So if we are able to measure the built-in capacitance, right, the depletion capacitance across different bias potentials, right, across the PN junction, it gives us the slope of this curve, gives us what is called as the actual doping density. Now it is also true that this expression is general. It is not especially only for the abrupt profile that we considered. For any profile, this d by dv of 1 by c square, c being the capacitance which is measured, right, is 2 by q epsilon s, the density at the edge of the depletion width W, right? For any applied potential V, right, you have a depletion width W, and the doping density at the edge of this width W is this expression, right? So basically, this expression or this measurement can tell you experimentally what is the doping density at various widths from the junction, right? And if we take a particularly simple PN junction which is kind of one-sided, right? So let us say if I have a very high doping density ND and very small doping density NA, the width is approximately equal to NP, right? Because XN is much smaller than XP, so the width is mostly about XP, and NB will turn out to be only NA. Right? So with these reductions in the number of variables that we have, we can very easily determine what is the doping profile we have in this lightly doped region. Right? Now let us take a look at some measurements and then see how this particular expression is useful for researchers or people who are working in the industry. Right? So here is a measured capacitance versus voltage, right? You can see this, that the capacitance is shown here, right? So as your reverse bias potential is increased, your capacitance actually decreases, which is understandable, right? Your width increases, so basically it is epsilon by width, so your capacitance value should decrease. After a particular level, the capacitance value do not change a whole lot because you're almost depleted the entire region, right? And the 1 by c square value at every potential, so you can from this measured capacitance you can actually calculate 1 by c square, and then if you plot this, right, at each value the slope of this curve is plotted here. The slope of this, you can calculate the slope of this curve at each value of x, right? And from this slope you can extract what is called as a doping density. So people typically extract the doping density versus the depletion width micron. So you go at different depletion widths, 0.5, 1, 1.5 and see, and then see that if I have a PN junction like this, and then I have a N which is super heavily doped. Now I'm looking at the doping density from this x is equal to 0, right? Because N is considered to be super heavily doped, so you do not have any depletion on the N side. I'm looking at the doping density on this side. So you can see that from there is some missing information here. We will see why you do not get much information here. Very close to this junction you do not see many information, right? And after that you can see that after 0.5 you can see that the doping density is almost constant, and then you have a very sharp doping profile at about 1 to 1.5 micron. So you have a very high doping density here and reduced densities in these regions. When you see this, can you tell me what kind of a doping that they could have done here? Could it be ion implantation, or could it be solid state diffusion? What kind of doping technique will give you this kind of a profile? I will let you think about it. Right? Now there is a reason why there is not much information very close to the heavily doped region. This, you typically do not get information about the heavily doped region for a distance LD. LD, as we previously saw, is called as a day by length, because any region, because the actual potential is screened within the region of this LD, right? So whatever measurement that we did, if let us say that if we have our potential applied such that the depletion width is close to this LD, right, you will not see you will not see a lot of information here, because of the fact of that it is lesser than the d by length. Also, the width is now a summation of the depletion width in the N as well as the depletion width in the P, which is now both at similar levels, right? So you do not get much information close to the junction because of the fact of having screened by the heavily doped N region, as well as the fact that you will have much similar values of Xn and Xp close to these interfaces, right? So at this point we will stop, and the next time we will meet, we will talk about the ideal diode equations and so forth.